Today, our topic is structure properties of metal and non-metal. My name is Lu Junxi. I'm from DAT J1. First is the introduction. Metals and non-metals are two separate sorts of materials that we encounter every day. Metals and non-metals are the two types of elements, and knowing whenever an element is a metal or a non-metal is crucial. Non-metals are insulators, while metals are good conductors of heat and electricity. Materials are classified according to their qualities as seen above. The metal structure properties. Metal account for about two-thirds of all the elements and about 24% of the mass of the planet. They are all around us in such forms as steel structures, copper wires, aluminium foil, and gold jewelry. Metals are widely used because of their properties: strength, ductility, high melting point, thermal and electrical conductivity, and toughness. These properties also offer clues as to the structure of metals. As with all elements, metals are composed of atoms. The strength of the metal suggests that these atoms are held together by strong bonds. These bonds must also allow atoms to move, otherwise how could metals has hammered into sheets or drawn into wires? As reasonable model would be one in which atoms are held together by strong but delocalized bonds. First is bonding. Such bonds could be formed between metal atoms that have low electronegatives and do not attract their valence electrons strongly. This will allow the outermost electrons to be shelled by all the surrounding atoms, resulting in positive ions surrounded by the C electrons. Because these valence electrons are shared by all the atoms, they are not considered to be associated with any one atom. This is very different from ionic or covalent bonds, where electrons are held by one or two atoms. The metallic bonds in therefore strong and uniform. Since electrons are attracted to many atoms, they have considerable mobility that allow for the good heat and electrical conductivity seen in metals. Above their melting point, metals are liquid and their atoms are randomly arranged and relatively free to move. However, when cooled below their melting point, metals rearrange from form ordered crystallized structures. The next one is crystal. To form the strongest metallic bonds, metals are packed together as closely as possible. Several packing arrangements are possible. Instead of atoms, imagine marbles that need to be packed in a box. The marbles will be placed on the bottom of the box in neat orderly row, and then a second layer begun. The second layer of marble cannot be placed directly on top of the another marble, and so the row of marble in this layer move into the space between marble in the first layer. The first layer marble of can be designated as A and the second layer as B, giving the two layer of designation of AB. Packing marbles in the third layer required a decision. Again, Rows of atoms will nest in the hollows between atoms in the second layer, but two possibilities exist. If the rows of marble are packed so they are directly over the first layer, then the arrangement could be described as ABA. Such a packing arrangement with alternating layers would be designated as AB-AB-AB. An AB-AB arrangement is called hexagonal closed packing. If the row of atoms are packed in this third layer so that they do not lie over atoms in either the A or B layer, then the third layer is called C. This packing sequence will be designed ABC ABC. So, and it also called known as face-centered cubic. Both arrangements give the closest possible packing of spheres, leaving only about a fourth of the available space empty. Now is a non-metal structure properties. The structure of the non-metals differ dramatically from those of metals. Metal crystallize in closely packed arrays that do not contain molecules of covalent bonds. Non-metal structures contain covalent bonds, and many non-metals consist of individual molecules. The electrons in non-metals are localized in covalent bonds. In a metal, there is delocalization of the electrons throughout the solid. The noble gases are all monatomic, where the other non-metal gases hydrogen, nitrogen, oxygen, fluorine, and chlorine normally exist as the diatomic molecules H2, N2, O2, F2, and Ci2. The other halogens are also diatomic. Br2 is a liquid, and I2 exists as a solid under normal conditions. The changes in the state as one moves down the halogen family offer excellent example of the increasing strength of intermolecular London force the increasing molecular mass and increasing polarizability. Oxygen has two allotrophes, O2 dioxygen and O3 ozone. Phosphorus has three common allotrophes, commonly referred to by their colors white, red, and black. Sulfur has several allotrophes. There are also many carbon allotrophes. Most people know of diamond, graphite, and charcoal, but fewer people know of the recent discovery of fluorines, carbon nanotubes, and graphene. So this is the end of the slide. Thank you.